All right, everybody, we're going to continue our exploration of mechanisms from Chem 242 Fall 21 Test 2. And here we go with a diazomethane esterification. In this one, you've got to realize that diazomethane needs to become a CH3 instead of a CH2. And the ester needs to, the carboxylic acid needs to lose its proton. I wonder where that proton went. Well, it went to the CH2. The only reason that is a minus on the CH2 is because it has a lone pair. Better put it on there because you need to use it. And better start your mechanism on the lone pair. Acid base. You generated a carboxylate. Moderate nucleophile, and diazomethane. That is a methyl with the absolute most exceptional leaving group ever. Nitrogen gas is about to happen. Backside attack, leaving groups leaves. That's the reason this is only 3 points. Because we're done. Love that one. Okay, ester reduction by DIBAL-H, diisobutyl aluminum hydride, right here. Here the H minus is generated, but the only reason it's really generated is the carbonyl is there to make a bond to the aluminum. H minus won't happen on its own here because that species is neutral to start with. And aluminum, with only 2 groups on it, not a happy aluminum, so it doesn't happen. And what you have here is your aldehyde almost. Still got stuff on it. It's got the O. It's got the aluminum with 2 isobutyls. And what else has it got? It's got a new H. It's got an OCH3. You don't have to show me the new H. It's right here. Right there. So step 1 is over. If this was lithium aluminum hydride, you'd have work to do still. And this one, step 1 is over. HCl is there. Protonate your leaving group, so why don't we do that? In fact, I think I'm going to improve on the classroom version of this mechanism. If you want to use the classroom version that we did the other day, it's fine. But here, it's the keeping with the theme. Sometimes you need to protonate your leaving group, and then it can be pushed off after you protonate it. And you have to acknowledge blue second. Hey, I don't even have to say red first if I say blue second. How's that? Then you've got an intermediate. And let's draw the intermediate. What do we got? We got an oxonium with an aluminum on it. That's a terrible IBU too. Much better. And what else do we have? We have a Cl minus plus charge. And don't do a backside attack on aluminum and make it leave. You can do it like this. No, don't do red, blue first. Do it like this, red first. But don't pretend aluminum knows how to do an SN2. It's a second step. You make a 4th bond, then you break a different 4th bond. That's aluminum's nature. Okay, so pick this one or the one we did in class to make your favorite. And I am going to say red first. It's not sitting with me well there. And then we'll do the Aldol reaction. The Aldol reaction makes bonds to the alpha position of an aldehyde or a ketone. It's a little more general than that. It makes bonds to the alpha position of any carbonyl. We got hydroxide, a base, and the alpha hydrogen. It's not a pKa favored reaction, and we'll talk about that in lecture. Or you can watch the existing videos on it already. The fact that it isn't favored by pKa is actually to our advantage. I love that. Unfavorable equilibrium means that arrow's smaller. Big arrow's backwards. Big arrow's backwards, small arrow forward, just tiny. And we have this species here. And it's surrounded by unreacted versions of the same aldehyde. How do I know that? Well, pKa says when I made water, pKa 16, from something that started pKa 20, I have a ratio of 10 to the power of 16 and 20 is a difference of 4. I have 10,000 of these for every one of these. Hey, this guy's surrounded by 10,000 unreacted aldehydes. Guess what it's going to react with? One of the 10,000 unreacted aldehydes. So don't ask where the unreacted aldehyde came from. It's exactly that, an unreacted aldehyde. And step 1, you're going to generate an O-. Step 2, you made water back in the day here. Step 2, the O- you're generating here is going to protonate and generate an aldol product. We'll continue the purple to the right. I want to keep the top of the screen in mind still. And the aldol, not only is it the most important reaction in chemistry, it actually has a name that I like. You don't hear me say that every day. New bond. Why do I like the name aldol so much? Look at this product. It has 2 extra carbons, 3. Okay. It's got an aldehyde and an alcohol. Aldehyde, alcohol in the same molecule, called the aldol product. I'd like to point out that I have 2 arrows going different directions from the same molecule. That's confusing. But I wanted to point out something else. Yeah, this reaction works with aldehydes and ketones. So don't be too sad that it's still called an aldol reaction, even if this was a ketone, which means there would be a ketone here and an alcohol. They used to try to call it the ketol reaction, and then chemists said, why? It's the same reaction. Don't do that. So we went to aldol. And what do you do with the aldol product? It clearly doesn't look like the final product, but it looks a lot like it. What's the difference between this molecule and this molecule? Well, I'd like to point out there's an alpha H here that is not in the final product. You better show it because it's got to disappear. I'd also like to point out that in the beta position here, yep, that's beta. You've got alpha for 1 away from the carbonyl. Beta is another 1 away from that. And when you're done with an aldol condensation, you have a double bond between alpha and beta. How do you do it? Well, you got to use a base again. This is base number 2. Meow, meow. grab H, sigma becomes pi. Yes, you're allowed hydroxide leaving groups and mechanisms that start with hydroxide. All these things seem to be said earlier. Yeah, they were said in the previous video. Yeah. And there you have the Aldol condensation product. Aldol condensation product. And at this time, we're going to stop this video. Going to come back with Allie for a chat to figure out what we're going to do on our next one. We'll wait for that.